Hello everybody, welcome back. This is Alex Does Lead Code, where I do programming problems on stream with you. As usual, the best way to learn from this channel is to work on these problems yourself and then see what the solution is. See some definition of solution, and watch what my thought process is in getting to a solution. If you don't have time, of course, the second best option is just follow the live stream and see how things go. Okay, with that said, let's dive into today's problem right away. Today, we're going to be working on the problem called Sudoku. We're going to be working on the Sudoku problem. Hold on. Let me adjust some settings. Give me 1 second. Okay, with that said, okay, I was seeing myself on the channel. Okay, so as I mentioned last time, I'll be monitoring chat more closely now that I have that enabled. So feel free to jump in the chat, talk to me, talk to each other, and let's all have fun. All right, so today's problem is number 36. It's called valid Sudoku. And it goes like this. Determine if a 9x9 Sudoku board is valid. Only the filled cells need to be validated according to the following rules. Each row must contain the digits 1 to 9 without repetition. Each column must contain the digits 1 to 9 without repetition. Each of the 3x3 sub-boxes of the grid must contain digits 1 to 9 without repetition. So essentially, I don't know if everybody here is familiar with the game of Sudoku. The game of Sudoku looks something like this. You have a board like this, some numbers are filled out, and your job is really to fill in the rest of the numbers. And you have 3 constraints, which is 1 for every row. Every row needs to have 1 to 9. So this row has 5, 3, and 7. You have to put the remaining numbers 1, 2, 4, 6, 8, and 9 in these empty boxes. And you can't repeat any of them. Likewise, every column has to have the numbers 1 to 9. So this has 1, 3, 6, 5, 9 in it. There's 2, 4, 7, 8, which go into these 4 boxes. And third rule is each of these 3x3 sub boxes, must have the numbers 1 to 9 in them, with no repetition. All right, this sounds like it sounds like, it sounds easy, but it really is not. It really is not, especially when you start with Sudoku boards that don't have as many numbers filled in. So let me turn off this. Okay. That don't have as many numbers filled in. So today, all we have to do is, given a board, we need to check if the current state of the board is valid. So we're only looking at filled numbers. So in this case, our job is to check for each row, for each column, and oh, that is a very bad column. And for each of these 3x3 squares, whether they obey the 3 rules, which is they have the digits 1 to 9 in them, with no repetition. I think at some points I'm going to do a video on writing a Sudoku solver. That's a much more difficult problem. That program will essentially get a board like this and try to fill in all the missing numbers. That's actually not easy. But today, all we're doing is to check if the board is currently valid. Okay? And that's not as difficult. So let's think about what we need to do this. So I actually like this problem a lot because it's not a tricky puzzle problem. It's more of an engineering problem, right? There are no clever things that you need to do. All you have to do is to write code that follows a set of specifications. So essentially, let's start by, as usual with a large complex problem, we'll start by breaking it down, right? There are three things we need to do. First, we have to check that every row is valid. We need to check that every column is valid. And third, we need to check that every let's just call it a square. The small, I know the big one is also square, but let's call these small ones, these 3x3 ones, also square, aka a 3x3 box is valid. Okay, we have 3 steps. These 3 steps, intuitively, I think they are largely independent, but they have a lot of overlap in terms of logic. So that tells me that we are going to write some kind of helper function that's going to be common to all of them. But structurally, each of them is going to check things in fairly independently. Now, as we solve this problem, we might find that there's even more cross-pollination between these 3 tasks than we originally envisioned. In that case, we can change things up a little bit. But right now, I don't see how they can cross-pollinate. I don't see how you can check each column quicker based on the results of checking each row. But that's just me. Let's start with the row first. So we're going to iterate through. We have a board, which is 9 by 9. So we're going to iterate through each. Let me see. Okay, the board looks like this. It's a 2-dimensional list. Okay, so let's iterate through this board to pick out all the rows. Row in board. Okay. So getting the column is actually not easy. The row is easy. Row. That's not true. Actually, getting the column is easy too. Okay, so for each row in board, what we're going to do is to say each row in board we are going to do is to check that the row has 9 numbers and all of them are valid. So this is actually not difficult because we're going to use. So the reason why I'm pausing is I'm thinking of Pythonic functions, right? So step 1, we need to collect all numbers in this row. And then step 2, check that there are no repetitions and none of the numbers, all the numbers between 1 and 9. Okay, that's not too hard. So collect all numbers. We've already done this by default because we already have this list. But this list is not actually right because of these dots. So we need to get rid of the dots somehow. We need to get rid of the dots. So I think the best way to do this, numbers equals row we're gonna get a list okay, let's do it the old-fashioned way. For n in row, if n is not between 1 and 9, then you can return n not n equals to dot, then you can return false. Okay? Let me see if I can write this in a better way. If n equals to dot, if n is just a placeholder, well, I'm going to continue. If n is not between 1 and 9, oh, and interestingly enough, n is a string. N is not a digit, so we have to do that conversion at some point. So if n is not between 1 and 9, then I'm going to return false. Num equals int n. Okay, so we are going to check first. We're going to ignore all the dots. And second, everything that's not a dot and not a digit, return false right away. There's something wrong with the grid. Okay? And now we're left with the numbers. Num equals to int n. So we're going to put them in a... We're going to put them in a list. Let's call it nums equals nums plus equals int n. So nums is a list containing the integer version of n. So nums will be the integer version of n. So at the end of running this first row, nums will be 5, 3, and 7. Okay? After this for loop, nums will be 5, 3, and 7. Okay, so now we have to check if nums has no repetitions. That's all we have to do, right? Because we know that nums is of size 9. We're going to trust that the board is the right size. We also know that nums only contains digits. Now, if this board is of size 9 and only contains digits, then checking that it has no repetitions is sufficient. Yeah, I think basically that's the only thing we have to check. So to check that nums has no repetition, the way we actually don't need this integer n, but we'll fix it later. Okay, let's get this thing to work first. So check that nums.length. This is a little trick I learned the last time. I have to think a little bit more about whether this is the best way to do it, but right now I believe it is. So I am basically using the set class. I'm creating a set from nums, which would essentially remove all duplicates from nums. So I'm going to check that the length of nums, if it's the same as the length of nums with all duplicates removed. So sets nums create a set from a list. And if this is the same, then there are no duplicates. If they are not the same, then I can return false. If they are not the same, it means that there are duplicates. There are duplicates and can return false. Okay? Cool. So this is how I would check if the row is valid. Now let's check if each column is valid. It's going to be roughly the same thing. I think the only thing that changes is the first two lines. Instead of for each row in board, I'm going to say let's do an index for I in, okay, so x in range 9. For y in range 9. Oh, actually, there's a better way of doing it. There's a better way of collecting these numbers together, but we'll explore that later. So for x in range 9, for y in range 9, n equals to board x, y. Yeah, I just want to check whether I got the x and y right. Okay, for board x, y. So we're collecting everybody with the same x, but different y. So this is wrong. This should be yx. Okay, why did I flip this around? So what I was thinking of was I'm trying to get these guys. Okay, trying to get these guys right here. So 5, this 5 is going to be bought because it's going to be bought 0, 0. Okay, this was a mistake. Okay, it's going to be bought 0, 0, obviously. But what about this 6? 6 is going to be bought. It's the second row, right? So it's going to be 1. It's going to be 1, 0. And likewise, this, let's go all the way to here. This guy is going to be bought 8, 0. So you can see that the first number is changing. The first number tells you what row it is. Since it goes downwards, we're going to call this y. That's why I call it y. And the second number is fixed. It's always the first element in each row. So you can see that y is changing. In this place, y is changing. The code right here, y is changing, but x is fixed. Okay? When we're adding to nums, in this entire section, y is changing, but x is fixed. So this is what we're going to do. This one actually it can be written in this form too. I just need to flip the x and y around. Just need to flip the x and y around. All right. Length nums not equals length. Okay. So now, third one. Okay, we're gonna have more or less same thing, and this looks, if you look at this, you can immediately tell. Okay, you know what? Maybe there's a way to factor out similarities. Maybe there's a way to factor out similarities across these 3 blocks of code. Think about that a little bit. Okay, but let's work on the last one first. Okay, the last one is a little bit different. We want to get this. We basically want to get one of these boxes. So if we just do a for loop, we can't do it this way, right? So what we're doing in the 2 cases before is we are iterating on either x or y, and then we are collecting nums just outside of the inner loop. So we can't do it this way. Instead, what we have to do is a little bit different. So that I can think of 2 ways of doing it. One is I make nums an array of arrays. I make nums an array of arrays, and in the first step, I'm going to populate all the numbers into nums. So there's going to be 9. There are going to be 9 numbers in nums, and each of these, correspond to one of these squares. And that will make my life a little bit easier when collecting it. The downside of doing that is then I have to keep a little bit more data around. Okay? I have to keep a little bit more data around. Now, if I were to think about this problem, right? In this case, Sudoku, it doesn't matter, it's 9 by 9, right? Easy peasy. But in the general case, if I want to scale this to a very large number, if I'm going to scale this to a very large number, this can be, billions or trillions or whatever, some huge number. I don't want to keep that many things around because that's going to cost memory. Okay, that's going to cost memory. So in this case, it doesn't matter. But imagine if you have a Sudoku board that's extremely large, right? Then keeping a lot of things around, keeping a lot of this kind of intermediate data around, collecting all the squares before testing them would actually cost memory. So I'm sort of waffling between the two strategies. You know what? Let's do it this way. Because this problem is Sudoku. Let's just assume that it's a 9 by 9 grid. Let's just assume it's a 9 by 9 grid, and then we'll check the numbers this way. Okay, cool. And I think that also makes it easier to tie back into the other two steps. All right, so nums equals to this. Okay. So let's see. We are going to have we're going to turn nums into a dictionary. So the idea here is that when we are at board yx, we're going to figure out which subsquare we're at. Right? We're going to stick it in the right subsquare. So we're doing a funny thing where we are going number by one number. And so it's not always easy. It's not trivial, I would say. It's easy, but it's not trivial to find out which subsquare you're in. You have to do some math. But if we're lazy, we don't want to do the math. You see, this is subsquare 1. This is subsquare 2. So it's 1, 1, 1, 2, 2, 2, 3, 3, 3, 1, 1, 2, 2, 3, 3. So it's a bit of, it's kind of gets a little uncomfortable. Okay, so let's say, let's say we are just going to, okay, let's name these subsquares. Let's call this 0, 0. Let's call this 1, 0. This is 2, 0. This is 1, 1. 0, 1. 2, 2. Let's name all these subsquares. Okay, let's name these 9 subsquares. So our first task is to figure out which subsquare we're in, which square we're in. Square equals, and to do that, that's not super difficult. We just do so x / 3. We do the string version of plus string of y / 3. Okay, and this will give us the subsquare. It's technically the other way around. Yeah, let's do it properly. Let's do it this way. So square is basically which the label which square we're in. Okay, and then we go to nums. If not square in nums. So if nums does not contain squares, then nums square equals to empty array. Plus equals to n. Okay, cool. So this should work. I'm fairly confident this should work. This should actually give you... Okay, so let's quickly recap what this does. It collects a number. It does some preliminary checks. And then it determines which square this number belongs to. Once it's done that, it adds that n into the square nums. So at the end of running this block of code, nums will look like this. It'll look like square 0, 0. And this is a string because of what we did here. Okay? And square 0, 0 will have 5, 3, 6, 9, and 8. 5, 3, 6, 9, and 8. So square 1, 0, which is here, 1, 0, will have 7, 1, 9, and 5. 7, 1, 9, and 5. Right? So this is square 0, 0. And then this is square 0, 1. Sorry, 1, 0. And then so on and so forth until we have all 9 squares. And notice how these numbers are collected together in their own little subsquare. Okay? And once we've collected these numbers, we can do the same thing as we did before, which is... And now we do a for loop because nums contain multiple things now. For nums dot values, if length of s not equals to length of sets of s, return false. Otherwise, we're done. Okay, I'm pretty confident this should work, but let's run it. Oh, okay. So because n is a string, I have to do this. Notice that this will still work because n as a string has to be between 1 and 9 as strings. So this will still work whether these are integers or strings. And it's not iterable. Plus equals, is it a pen? I think it's a pen. Okay, so let's run it. Let's fix the bugs. Syntax errors. Oh, judging. Oh, there we go. Let's submit this and see how fast it works. I'm still gonna work on this after submission. Okay, so it beats. Okay, it beats half of. It's about average. But notice how we use more memory than other people. Okay, we use more memory than other people. In this case, I don't care because the amount of memory you use is by definition fairly small. It's a 9x9 grid. There are no, scaling versions of Sudoku. Okay, so we're gonna stick to this, but we are going to do something. We're gonna make this a little bit nicer. Notice how there's a lot of repetition in our code. You see that this part is all repetition. This part is all repetition, right? These things are all repetition. We're going to rewrite our code, or we're going to refactor our code, so that there is less repetition. Okay, that we want to make sure that there is less repetition. So there are two principles I want you to take away here. One is feel free to always write a version that works first. So notice how I started with version that works, and after I have a version that works, I'm going to improve it. You don't have to do something that's perfect right away. Okay? We don't have to do something that's perfect right away. Okay. So the second principle is when you're refactoring, you should look for the most general case and start from there. Right? As we were writing this, one thing I noticed, I didn't think about this before, but one thing I noticed is that things got harder and harder, more and more complicated as they went along. Finding duplicates of rows is really easy, and then columns is a little bit trickier. You have to do this board XY thing, 9 and 9. And then finally, this one is the trickiest because square is a little bit more arbitrary. So this tells me that the best way to do this, or at least the sort of, engineering, the sort of nice way to do this, is to start with the most general version of the problem and then work from there. So this is the most general version, which is I have some kind of dictionary for nums. I am going to collect numbers and put them into these dictionaries. And then I'm going to sort them and just drop stuff. Okay, so this is the most what's the word for it? This is the most general version. All right. So how am I going to change this to make it work to include both rows and columns? Well, it's fairly straightforward. So right now, nums is a dictionary that maps from the square, the name of the square, to a list, right? We can just modify this to do the same for rows and columns. So we can do square equals to, let's just call it square plus this. Row equals to row plus, and row is basically y, right? Yeah, it's y. Column equals to column. Oh, row is x. I'm sorry. So this always gets me. Personally, this always gets me. This like x and y thing. I put x on the outside. This would be a lot easier if I put y on the outside, which I probably should. This is so much easier now. Okay, cool. So y on the outside, yeah, it's because of the way this works. The outside refers to the index of this row, right? So the outside, yeah, well, it's the way it works, basically. board X. Okay, I gotta think about it later. I think this is actually YX. If I'm not mistaken. Yeah. Okay. Yeah. So the first index is actually the thing you iterate over first is actually the Y. So this is the Y. The Y-axis as it goes down. And the X-axis as it goes to the right. Okay, cool. So I have row, column, and square. So if not square and num, square equals and I do this for rows and columns. So essentially what I'm doing is I'm taking this number, right? I'm taking this number, I'm sticking it into 3 separate indexes. 3 separate places. And at the end of one of these iterations, let's say at the end of this 5 over here, the first iteration of 0, 0, which is this 5 over here, which is 0, 0, square nums will be equals to, okay, actually, yeah, nums will be equals to, nums will have 3 things in it. You have square 0, 0, colon 5. It will have row 0, colon 5. And then it will have column 0, colon 5. Okay? And as we add, now we add the number 3. Number 3 is also square 0, 0. So I'll get 5 and 3. It's also row 0. So 5 and 3. But it's column 1. So we'll have one more in column 1. And this is how it's going to work. Right? This is how it's going to work. And we're going to keep appending. And the end of this should work exactly the same as it did before. You can see how this piece of code is smaller and hopefully a little bit more readable than the one before it. Now I'm going to make this a little bit, this is just going to make it a little bit easier to understand. So in general, I like to localize concepts. So this concept is to square. This concept is add to row. And then this concept is add to column. So previously, I had my column all the way up here, which is not what I want to do. I want to separate these things. And now let's submit this and see what happens. I think this should work. But it's going to take more. It does not take more memory. It takes about the same amount of memory. That is interesting. I did not think that was the case. I didn't think that was the case. And that's because I actually added more things. I added more things to nums, which means I'm persisting more things in nums. But I think that's so the reason the fact that these two things don't differ that much suggests to me what's really happening is that this nums is not taking a whole lot of memory, because if you think about it, this is very small. This is like really, really small. It's not gonna take a megabyte. It's not even 1 kilobyte, right? Maybe 1 kilobyte. I'm not sure. I didn't do the math. But these are all fairly small. I don't know how big an integer is in Python. But I can't imagine it being more than a couple of bytes. So altogether, and these squares, this is like 10 bytes or whatever. So altogether, it's not going to even take 1 kilobyte. So that suggests that the amount of memory used in nums is not a big part of the total amount of memory used. In fact, it's a trivial part. It's a rounding error, which means that I shouldn't be concerned about the memory used in nums. That said, this is only true because Sudokus are 9 by 9. If we're going to scale this up, then we will absolutely be concerned with memory. Okay, so I think this is okay. So I'm fairly happy with this solution. I'm curious what other people do. Brute force easy approach. What do you mean by brute force? Okay. Okay. So this is checking rows and columns, yeah. And then this is 9 by 9. Oh, I see. So this is the other way of doing it. So what this person does is this nested for loop checks the rows and columns. It checks the rows and columns. And this thing over here checks for the 9 by 9. So you see that this is I plus 3. So I is 0, then I is 3, then I is 6. I see. So this person basically for each of these, it's each box. And then it does this 9 by 9 inside, which is another way of doing it. This would take up less memory than mine. This is the way I would have done it if I wanted to save on memory, but it turns out that memory is not a huge concern. So again, another lesson takeaway is do not prematurely optimize. Okay, cool. Now I think that's all that we have for today. Let's figure out what is the next problem to solve. Let's come back to problems. As you guys know, I am a sucker for cool sounding names. Let's pick something that we have not done before. These have no cool names, but it is, I see, hard. Let's try one of these hard ones. So minimum window substring. Substring with concatenation of all words. Okay, let's do this one. This seems like one of the puzzle problems. Unfortunately, this is exactly the kind of problems that I kind of dislike. It's complicated. How do I like this? There. It's complicated and it's abstract. And I'm gonna bet there's some kind of trick to doing this right. But either way, let's leave that for next time. I do like it, however, because it is a difficult problem, and unfortunately, in many of these like leak code interviews, they will give you this type of trick problems with a lot of complicated permutations. Okay, so that's all for today. See you guys next time.